In this video, I'm going to talk about Poisson regression. Poisson regression is useful when you're working with counts and rates, and that's a pretty common form of data for cohort studies, where you're ideally trying to look at the number of events over time, and that's kind of one of the key aspects of a rate, is that it's something over time. It's also useful when whatever the outcome is can happen multiple times to a person, like number of kids a person has, or number of car crashes over an individual of time, or over a period of time. And yeah, so the Poisson distribution is, it looks like this. The y-axis here is the probability of a count, and the x-axis is these possible counts. So the probability of having 0 events happen over time is low, because here the mean is 3.4, so that's the most likely number of events to happen over a span of time. And the fact that all of these really high number of counts are possible but unlikely is what gives it this like really skewed distribution, where it's not unheard of to get 13, but since the mean number of events is 3, it's unlikely. And this is kind of similar to a binomial distribution, and actually as the mean gets larger, it starts to kind of approach a binomial distribution. And a binomial distribution, just to review, is defined by like a defined probability of an event happening. Like a coin flip, the probability of heads is 0.5, and it's also defined by a number of trials. So here it would have been better if I just made the mean like 5, because then I could do the example where if we did 10 coin flips, it's likely that we would get 5 heads. We probably wouldn't every time, because like just a random chance, but if we were to do this a bunch of times, we would most likely get 5 heads out of 10 coin flips. But yeah, so as the mean increases, the distribution starts to get a little less right skewed and starts to approach binomial. And as it gets even larger, like above 10, it starts to look more and more normal. So like I was saying before, a rate is a number of events over time. In epidemiology, we usually call this incidence, and incidence is the number of events over person time. It's represented by lambda here. Lambda represents a rate, and this hat means it's an estimate. So the rate, or the estimated rate, is the number of events, y, over time, t, and we typically represent time as person time, and I'll just give I have a whole video on that, but I'll give like a brief description of that. Oh, first, yeah, just talking about where that comes from in like a data table. This is a data table where we have exposure positive, exposure negative, and the number of events in each group, and the person time they were followed. So to get a incidence ratio, we could find the incidence in the exposed group, number of events over time followed, divided by the incidence in the unexposed group, number of events over time followed, and that comes out to an incidence ratio. So an estimate of, sorry, that's not that. That would be like lambda 1 over lambda 2 would be an incidence ratio. So this is the description I was talking about from my other video that gives like an overview of person time. So if we followed this group of people for 4 years and we saw 2 events, a crude rate would be 2 events over 4 years. But you can see here that some people had events earlier and some people had their observation end before the follow-up time was over. So we can account for that with person time, where with person time we count the amount of time each person contributed before they stopped being followed, where this person, we stopped following them because they dropped out of the study or whatever, and this person we stopped following them because they had the event. And just to specify, this would be an example of when they can only get the event once, like chickenpox or something, where they get it after year 2 and there's no point to follow them anymore because they're not at risk. Well, if we add up the amount of time everyone contributed, we get 13 years, so instead of just doing 2 over 4, we can now do 2 over the number of person years and get a more accurate estimation. 2 things to notice about when this data structure is applicable to Poisson is The probability of disease needs to be stable over time, so we can consider this person's 1 year of contribution as much of a risk as this person's. So if all of a sudden something changed after year 2 where the risk of disease just ramped up, this data would no longer be applicable because we can't consider this person's time at risk equivalent to this person's. Another key assumption is that people who drop out are dropping out at random. They don't differ from those who remained in the study. So this person dropped out while this person remained further. It would be a problem if this person dropped out because maybe they got like really sick and didn't show up to the appointments. All of a sudden, your data is biased, so you need to be able to defend the assumption that people who dropped out at random. So this is kind of a description of the Poisson model with only one covariate. So we have our rate equal to exponentiated b0 plus b1x. But what we typically do is take the log of that. That's the link function. And a link function is what we do to the outcome to put it on a linear scale. So now we have a log linear function where we have our intercept on our one covariate. So how is the rate changing as a function of this baseline rate plus whatever covariate we're looking at? And just rearranging that, like I said before, this rate is a number of events, mu, over time. I don't know if I said that yet, but yeah, we represent mu as like the mean number of events. So a rate is events over time. But we can do something with that time in order to account for it in the model. We can multiply it over, and because it was log time, it's still log, so we multiply it over to here. And let's talk about what is in this model. So we have log mu, log of the mean number of events, and that is the intercept. If you remember just a formula for a line, we have our intercept, like where the line begins, in addition to this covariate that is the function of how our line is changing over x, so how our outcome is changing for each unit increase in x. That's what b1 is defining. It's kind of like it's a slope. But yeah, beta naught here is our intercept, and in this situation, y is a log number of events, or technically, since log t is free to move back over here, it's not a covariate. It's our baseline rate is how we can interpret it, or yeah, baseline log rate, because to get it as a rate, you'd need to exponentiate it. So yeah, beta 1 is our change in log incidence caused by x, and when we exponentiate that, and the reason we're exponentiating things here is because it's on a log scale right now, and that's just put it in a linear format, but we're not interested in it on a log scale. So to get it off that scale, we exponentiate it. And when we exponentiate beta 1, we get our relative risk for the influence of x on this relationship. Log t is something that is unique to Poisson regression. This is called the offset term, and this is basically how we account for person time, and it's what makes it a rate rather than like a proportion. And I'll get a little bit, it's kind of a very kind of hard to wrap your brain around sometimes, but for the sake of Poisson regression, I'll just describe what this looks like in the data, and then you don't really need to worry about it again. But something that is worth knowing is why beta 1 represents the relative risk, or the incidence ratio. So we described our model initially, where if we took the log of this e would cancel out and it would just be beta 1 plus, or beta naught plus beta 1. But yeah, let's just look at when beta 1 is present. We have the whole function being the intercept plus beta 1. But when beta 1 is absent, we have just beta naught. There's no beta 1 term. And the incidence ratio, like I said before, is the ratio of the rate when beta 1 is present over the baseline when it's absent. And if instead of just putting the lambda here, we put their whole equation, we have exponentiated beta naught plus beta 1 just over exponentiated beta naught. And due to exponent rules, we know that that's really just exponentiated beta 1 times, or exponentiated beta naught times exponentiated beta 1, and then these cancel. And then we're just left with exponentiated beta 1 equaling the incidence ratio. And you might be more familiar with relative risk. That's kind of synonymous with incidence ratio. So estimating beta naught, that's what we're interested in most, is if this was something like smoking and lung cancer, we'd be most interested in the relative risk of smokers and non-smokers. So it's pretty straightforward when there's just one coefficient, like when there's not a beta 2x2, beta 3x3. When there's just one, you're able to find it pretty simply. I'll show that in a second. It gets more complicated when you're looking at like say there's like smoking and age and sex. All of a sudden you need software to do maximum likelihood estimation, where it's estimating each of these betas in the context of each other, and it's this really like labor intensive iterative process that we use software to do. But just showing what it's like when there's one beta. Let's just say we have this data where when X is present and X is some variable like smoking and events is some variable like lung cancer or whatever. So this is just our aggregate data where we have when X equals 1, in that group we saw 20 events and they were followed for this amount of person years. And in the group where that variable is absent, there were 65 events and they were followed for this amount of person years. So the estimation of beta 1 is just the rate ratio like we were talking about before, where it's just the rate in x1, so 20 over their person time, and over the rate of when x is 0, so 65 over its person time. That comes out to 0.33, and we're not interested in the log relative risk, we want just the relative risk, so we exponentiate that and we got a relative risk of 1.4. So that can be like let's just say we put this in a more understandable context. If this is smokers and non-smokers and number of emphysema events, I don't really know much about emphysema, I'm assuming it's something that can happen multiple times. We can interpret this as compared to non-smokers, smokers are at a 1.4 times greater risk of experiencing emphysema. Things are a little more complex in a multivariable model. So here we're looking at the relationship between sex, age, and number of car accidents. And this here is the baseline rate of car accidents, well, exponentiated. It's the baseline rate of car accidents as it is, just beta naught. It's the log rate of car accidents when age is held constant, so set to 0, which isn't really biologically possible. We could center it to make it more meaningful, but here I'm not going to. And it's also when sex is held constant, and what that looks like is when sex is set to the referent. So let's just say males are the referent, then X is 0 and this cancels, and age is 0 and this cancels. So that's the baseline rate. The coefficient for age, when exponentiated, is the relative risk of car accidents for every 1 unit increase in age. So for every 1 unit increase, or I guess 1 year increase, and when sex is held constant, so set to referent, and I guess male it makes it 0. And the coefficient for sex here, when exponentiated, is the relative risk of car accidents for females, because that's when X is 1, and when age is set to 0, so canceling that. So the baseline risk, the relative increase in risk or decrease. So here we have what our data would look like for Poisson regression. You'll notice here that I didn't really talk about the offset. By the way, that's what we call that, log t, offset. I'm not sure if I said that. This is what the data looks like. So each observation is one person. So this person's a 22-year-old male who had 2 crashes and was observed for 10 years. And the reason the amount of time these people were followed differs is because maybe they entered the study in the middle, or maybe they were lost to follow up earlier on than it ended. So like say it was a 15-year study, this person might have come in at year 5 and stayed till the end. And this person might have been in part of the first 7 years and then stopped coming. But yeah, that doesn't really matter. But what we do, you'll notice that's log time. So we take the ln of that. In statistics, log and ln are kind of synonymous. Don't attack me, statisticians, if you don't feel that way. But yeah, it's log of all these. And then, yeah, we have our multivariable model, and we would input this into software. I have a video on that for SAS. And our output would look something like this, and just interpreting these things one at a time. The exponentiated coefficient for age comes out to 0.9, and whenever the odds ratio or relative risk is less than 1, I usually divide or do 1 divided by that, and then it can be a little more easily interpreted. So for each 1 year increase in age, the risk of crashing is 1.1 times lower, or there's a 10% decrease in risk of crashing for each 1 year increase in age. The coefficient for sex here is negative 2.08-ish. When exponentiated, that's 0.13. So again, we divide 1 divided by that, it's 7.7. So the risk of being in a crash decreases 7.7 times if you are female, and also being female is associated with an 87% decrease in being in a crash. And if we were interested in you notice that these are all relative risks. If we're interested in just the risk of a car crash in individuals, say a 25-year-old male, we can take our formula here and plug in the coefficients, so we know what beta naught is, we know what the coefficient for age is, and we know what we want, 25, and we know the coefficient for female or sex, but also we know that it's male, and that's our reference, so this would just cancel. It's factored into the baseline here. So this would be what our equation would be, and it would reduce to just that. And notice that it's log this, so we don't want that. We want it exponentiated. So it would come out to a rate of 0.25. And I kind of said that, like you've noticed, I said that was like the expanded format, and there's an aggregate format. This is an aggregate format where basically we just grouped all of the observations that were treatment negative and treatment positive. Something I didn't mention that I should have is that in the Poisson regression, a key assumption is that the mean is equal to the variance, and I don't think it needs to be exactly the same, but they need to be kind of similar. That's just a property of the Poisson distribution. And if the variance is much greater than the mean, then this is called over-dispersion. And you can interpret over-dispersion as really large residuals when you do your diagnostics. A more insidious part of it is small standard errors, so you might get things significant that aren't really. Some potential solutions are if you are missing some really important variable that's really important to the relationship, then including it might help this over-dispersion. Also, there's a statistic outputted that is the chi-squared statistic divided by the degrees of freedom for the model, and if that's really large, that's an indication that there's some over-dispersion happening, and you can multiply your standard errors by that to inflate them. But if none of that is helping, if it's kind of beyond repair, there's a couple other distributions you can use besides Poisson. Negative binomial is one that is able to handle over-dispersion and not, I think it just doesn't have the mean equals variance assumption, and it can do count data. Another special scenario is if over-dispersion is being caused by 0 being extra common, where typically, if you remember my distribution earlier where the mean's 3, it kind of rises up to 3, but if 0 is an inordinately common event and then it goes down again and then it goes up again, then there's something you can do called zero inflated Poisson, and that can handle that.